Now that we know what a power series is, and we know how to find its radius and interval of convergence, we're going to look at ways we can construct new power series from ones that we understand already. Let's start by recalling that we can write the function f of x equals 1 over 1 minus x as the sum from k equals 0 to infinity of x to the k. That's because that is a geometric series, and so as long as the absolute value of x is less than 1, in other words, our radius of convergence is 1 and our interval of convergence is negative 1 to 1, we know that the function and the series are equal to one another. If we multiply this function by other functions, compose this function with other functions, and contemplate differentiating and integrating this function, we'll see that we can construct new power series from this existing one. Let's start by seeing if we can come up with a power series for the new function f of x equals x squared over 1 minus x, and then figure out the interval of convergence for that function. Notice that f of x is equal to x squared over 1 minus x is the same thing as x squared times the quantity 1 over 1 minus x. But we know that the quantity 1 over 1 minus x is the sum from k equals 0 to infinity of x to the k, with the interval of convergence for x from negative 1 to 1. We can bring our x squared inside using the properties of sums to rewrite this as the sum from k equals 0 to infinity of x squared times x to the k, which is the sum from k equals 0 to infinity of x to the k plus 2. So we have a power series expansion for the function x squared over 1 minus x. Let's look and see which values of x it converges for. We'll evaluate the limit as k goes to infinity of x to the k plus 2 over, plus 1 over x to the k plus 2. We're going to take the absolute value of that, but of course that just gives us the limit as k goes to infinity of x to the first. And so our radius of convergence is 1, and our interval of convergence goes from negative 1 to 1. We'll double check our endpoints. If we take the sum from k equals 0 to infinity of negative 1 to the k plus 2, that is going to be the series negative 1 plus 1 minus 1. That diverges. The terms diverges by the divergence test. The terms do not go to 0. Similarly, if we take the sum from k equals 0 to infinity of 1 to the k plus 2, that is also going to diverge by the divergence test. So our interval of convergence is in fact just negative 1 to 1. All right, let's look at another example. This one looks similar but has some differences. Here we're looking for a power series for the function f of x equals 1 over 1 minus 3x. We're still going to use the fact that the function g of x equals 1 over 1 minus x can be written as the sum from k equals 0 to infinity of x to the k, where x is in the interval negative 1 to 1. But we're going to notice here then that f of x is equal to g of 3x, which means that we can write this as the sum from k equals 0 to infinity of 3x to the k, which is then the sum from k equals 0 to infinity of 3 to the k, x to the k. That is a geometric series, so we know that it's going to converge for absolute value of 3x less than 1, which means that our radius of convergence is 1/3, And our interval of convergence is negative 1/3 to 1/3. All right, we're going to do another similar example. This one's actually going to be useful to us again in just a moment. So let's look at this one. We have f of x equals 1 over 1 plus x squared. Notice that if we contemplate again g of x being 1 over 1 minus x, then f of x is the same as g of the quantity negative x squared. So since g of x is the sum from k equals 0 to infinity of x to the k, again on the interval negative 1 to 1, we know that g of negative x squared is going to be the sum from k equals 0 to infinity of negative x squared to the k, which is the sum from k equals 0 to infinity of negative 1 to the k times x to the 2k. So we have an alternating series this time. Let's look at the radius of convergence. We're going to look at the limit as k goes to infinity of the absolute value of negative 1 to the k plus 1. This should be a k over here, times x to the 2k, 2 times k plus 1, all over negative 1 to the k times x to the 2k. That gives us the limit as k goes to infinity of negative 1 times x to the 2k plus 2 over x to the 2k, which is the limit as, k goes to infinity of the absolute value of x to the x squared, which is of course just x squared. And we want to know when that's less than 1, so we can see that our radius of convergence is going to be 1. And we're going to be looking at an interval that goes from negative 1 to 1. We're going to check our endpoints this time. We didn't need to do that in the last example because it was a geometric series, and we know that the radius of convergence of those does not include the endpoints. But let's check our endpoints here. Because we have this alternating series, we might get something slightly different. So if we look at our power series back here and plug in negative 1, we're going to get the sum from k equals 0 to infinity of negative 1 to the k times negative 1 to the 2k, which is not going to go to 0, so we're going to see divergence, our endpoints once again. And we'll see the exact same result for 1, except we won't have an extra negative sign. So both positive and negative 1 diverge. So our interval looks like negative 1 to 1. Let's take a look at f of x equals 1 over 1 minus x squared. We're not multiplying g of x equals 1 over 1 minus x by a power of x. We're not composing it with something. So we need to think about another way to see if we can manipulate our original power series in order to get a power series for this new function. So what we can notice is that if we take the derivative with respect to x of g of x, well, that is the derivative of 1 over 1 minus x, which is negative 1 over 1 minus x squared. So in other words, we know that f of x is the negative of the derivative of g of x. But g of x is just a power series, just a sum of a bunch of terms. So this is the negative derivative of the sum from k equals 0 to infinity of x to the k. The way that derivatives and sum works, we can write that as the negative sum of the derivatives of x to the k. We know how to take those derivatives, so we get the negative sum of k times x to the k minus 1. So we've figured out that f of x equals 1 over 1 minus x squared can be rewritten as the negative sum of k times x to the k minus 1, but we need to think about what the interval of convergence is for that. So let's take the limit as k goes to infinity of k plus 1 times x to the k minus 1 plus 1. Let's put k equals 0 to infinity on this guy, all over k times x to the k minus 1. Well, that gives us the limit as k goes to infinity of k plus 1 over k. I forgot some absolute values over here. That's bad form. So let me put those in. And then we get times x, which is just the absolute value of x. So we see again that we have a radius of convergence of 1. Our interval is going to go from -1 to 1. Let's check our endpoints. At x equals -1, we get the sum, or the negative sum, from k equals 0 to infinity of k times -1 to the k minus 1, and we know that that diverges by the divergence test, and we can see that for plus or minus 1, we're going to get divergence by the divergence test, so our interval is -1 to 1, same as our original power series. All right, we just used a derivative. Let's look at this next example, which is going to show us how we might use an integral. So we have f of x is equal to the natural log of the absolute value of 1 minus x. And again, we're contemplating the function, or the power series, g of x equals 1 over 1 minus x, which is the sum from k equals 0 to infinity of x to the k. Notice here that if we take the antiderivative of g of x, we get the negative natural log of the absolute value of 1 minus x, which is negative f of x. So we know that f of x is going to equal the negative integral of g of x dx. I should have put a dx over in this antiderivative. That was terrible notation. Which is then the negative antiderivative of the sum from k equals 0 to infinity of x to the k dx. Sums and antiderivatives can be shifted around, so we get the negative sum from k equals 0 to infinity of the antiderivative of x to the k dx. So f of x now is the negative sum from k equals 0 to infinity. The antiderivative of x to the k is x to the k plus 1 over k plus 1. But of course, since we're antidifferentiating, we need our constant. Now, let's look at f of 0. F of 0 is the natural log of 1 minus 0, which is 0. But we also know that f of 0 is the negative sum from k equals 0 to infinity of 0 to the k plus 1 over k plus 1 plus c. So that means that c has to be 0. So we can conclude here that f of x then is the negative sum from k equals 0 to infinity of x to the k plus 1 over k plus 1. Let's look for our interval of convergence. So we're going to take the limit as k goes to infinity of the absolute value of x to the k plus 2 over k plus 2 times, because we're dividing by the previous term, we're just going to flip this over, we get k plus 1 over x to the k plus 1. The k plus 1 over k plus 2 limit is 1, so we end up with the limit. We don't need the limit anymore, we just get the absolute value of x. And so we can see that our radius of convergence is 1. Our interval of convergence is going to involve -1 and 1, but let's check our endpoints. So at x equals -1, let's do positive 1 first. At x equals positive 1, f of 1 is then the negative sum from k equals 0 to infinity of 1 over k plus 1 which we know diverges. But f of -1 is negative sum from k equals 0 to infinity of -1 to the k plus 1 over k plus 1. That one converges. It converges because it's alternating. The alternating series test works here. This one is our harmonic series. The plus 1 does not change the fact that the harmonic series diverges. We could just rewrite this as the sum from k equals 1 to infinity. This is the same as the sum from k equals 1 to infinity of 1 over k. So, which we know diverges because it's harmonic. The reason this is interesting is that we now see that, so f of x is this negative sum from k equals 0 to infinity of x to the k plus 1 over k plus 1, and that was the same thing as the natural log of the absolute value of 1 minus x on the interval -1 to 1. This tells us then that f of -1 in particular is the negative sum from k equals 0 to infinity of, nope, not x, -1 to the k plus 1 over k plus 1. In other words, that is going to be 1 minus 1/2. I'm accounting for this negative sign here in all of these, plus 1/3 minus 1/4, and so on and so forth. But that's equal to the natural log of 1 minus -1, which is the natural log of 2. So we have this expansion of the natural log of 2 as 1 minus 1/2 plus 1/3 minus 1/4, and so on and so forth, which is interesting, I think. All right, this next example is going to have an interesting application just like the previous one did. First of all, let's remember that we saw earlier that we could write the function f of x equals 1 over 1 plus x squared as the sum of -1 to the k times x to the 2k. And let's see how that might be helpful to us now in writing a power series representation for f of x equals the inverse tangent of x. So let me change this to a g so that we don't are using confusing letters here. So f of x now is inverse tangent of x. And if we take the derivative of f of x, we know that that is 1 over 1 plus x squared. In other words, the antiderivative of 1 over 1 plus x squared dx is equal to f of x. So that tells us that the antiderivative of the sum from k equals 0 to infinity of -1 to the k times x to the 2k dx is going to be equal to f of x. So if we use what we know about antiderivatives, we can write this as the sum from k equals 0 to infinity. I can pull the -1 to the k out in front of the integral sign because it has no x's in it, so it's a constant. So we're going to do the times the antiderivative of x to the 2k dx. That is then the sum from k equals 0 to infinity of -1 to the k, and then if we antidifferentiate x to the 2k, we get x to the 2k plus 1 over 2k plus 1. And of course, we need a constant here. Well, f of 0 is the inverse tangent of 0, which is 0. And that has to equal then the sum from k equals 0 to infinity of -1 to the k times 0 to the 2k plus 1 over 2k plus 1 plus c. So we see again that c is equal to 0. So we now have this expansion. F of x equals the inverse tangent of x can be written as the power series, the alternating power series, -1 to the k over times x to the 2k plus 1 over 2k plus 1. And let's look at our radius and interval of convergence. The limit as k approaches infinity of the absolute value of -1 to the k plus 1 times x to the 2 times k plus 1 all over 2 times k plus 1 times 2k plus 1 over -1 to the k x to the 2k plus 1 gives us, do a little bit of algebra now, the limit as k goes to infinity of the absolute value of, we get a -1 there. We have x to the 2k plus 3 over x to the 2k plus 1 times 2k plus 1 over 2k plus 3. We can see that the 2k plus 1 over 2k plus 3 term goes to 1. So we end up with the absolute value of x squared here. So our radius of convergence, x squared, is going to be less than 1. When x is between -1 and 1, we have a radius of convergence of 1. We're going to look from -1 to 1. Let's examine our endpoints. So at x equals +1, we have the sum from k equals 0 to infinity of -1 to the k times 1 over 2k plus 1. That's an alternating series. Its terms are decreasing and going to 0. So that, in fact, does converge. And similarly, at x equals -1, we're going to have the sum from k equals 0 to infinity of -1 to the k times -1 to the 2k plus 1 over 2k plus 1. So another alternating series which is going to converge. So this time we can include our endpoints on our interval of convergence. So we know that f of x is equal to the inverse tangent of x is equal to that power series, this power series over here, for all values between -1 and 1. And we're going to see a really interesting result with that in just a second. Okay, we just saw that the function, the inverse tangent of x, can be approximated or is equal to the power series from k equals 0 to infinity of -1 to the k times x to the 2k plus 1 all over 2k plus 1, and that converges on the closed interval -1 to 1. Let's see how we might use that to estimate a value of pi. So let's look in particular at the inverse tangent of 1. Notice that is pi over 4. But using our power series, that is going to be the sum from k equals 0 to infinity of -1 to the k times 1 to the 2k plus 1 all over 2k plus 1. And that works because 1 is in our interval of convergence. So we can write out pi over 4, plugging in k equals 0, we get 1 over 1. Plugging in k equals 1, we're going to get -1 to the first power times 1 all over 3, so we get -1/3. Plugging in k equals 2, we're going to get a positive term, and then we'll get 1/5. K equals 3 gives us -1/7, and so on and so forth. Well, notice then that if we multiply both sides by 4, we get that pi is equal to 4 minus 4/3 plus 4/5 minus 4/7, and so on and so forth. Now, this series converges slowly, but it does eventually converge to the typical value we know of as pi, which I think is fun and interesting. So, wrapping this all up, we don't have any specific formulas to talk about this time, but we've seen that if we use function multiplication, function composition, and if we cleverly differentiate and integrate, we can take existing power series that we understand and we can create new ones, which have very similar intervals of convergence and radii of convergence as their counterparts.